So good morning, everybody. I hope you're having a good day thus far and you're ready for another exciting day in 317. Today we have quite a bit to cover as we're going to start talking about friction and incompressible flow. One thing I will note, a couple things before we jump into it is one, I'm going to go ahead and just kind of skip the discussion on microscopic momentum balances. You have some notes on it. I didn't really give homework, and I don't expect to write midterm and final questions around those topics. I will at some point try to post solutions to the examples I put in that lecture. But it's there, it's useful information, but it's not really applicable at this level, I would argue, in terms of understanding fluid mechanics. One thing I also want to note is this Thursday is the career fair, and I do believe it coincides with our class time. And so I will be canceling class on Thursday so that you all have time to attend that career fair because it is rather important, even though it is a virtual event. However, that means that we have even more information to discuss today because we're only going to have time to have one, maybe 1.5 lectures in terms of our discussions in incompressible flow. So I'll probably be going a little fast today to try to get through as much as I can so that you have all the information you need for the homework. But as always, if you need clarifications or if you'd like me to slow down, re-explain something, feel free to stop me in my discussions. So with that being said, I'll throw it over to my OneNote. We can go ahead and get started. And so today, we are going to be looking at incompressible flow, and specifically friction in incompressible flow. Now, friction, as we consider it, largely stems from shear forces that are exerted between the fluid-solid interfaces that happen in our flow systems. And this shear profile, as we consider flow through a pipe, can look something similar to this, where the maximum shear we see is at that solid fluid interface, and at the center line of flow, we have no real shear. And then this is our flow direction. Keeping in mind that we have the no slip condition, which implies, or which means, we see high shear stress at a fluid-solid interface. And so this shear stress resists flow, resulting in a reduction, excuse me, of energy in our fluid in the form of a pressure drop. So simply saying we have shear stress within our flow system that resists flow, and that robs our system of energy, which we can measure as a form of pressure drop. Keeping in mind, once again, this is frictional losses. And we also often call this skin friction. So the question then becomes, how can we demonstrate this loss using an energy balance? Well, if I was going to go back to my flow section, flow through a pipe, I have some P1 initially and some P2 final. And if I were to pick points at those same locations, I can write an energy balance like this. And then from here, I can ask myself, which terms can I neglect in my energy balance? Well, if it's horizontal flow, I can say Z1 equals Z2. And if it's a constant cross-sectional area, I can say U1 equals U2. And if I don't see any pumps or anything, I can consider the work negligible, or that there being no work, which means I have P2 over rho plus friction equals P1 over rho, which implies any change in pressure that I'm seeing in this system must be a result of friction. And often at times we can call this delta PS for skin friction. Sometimes I write it like that, but it's quite rare. So, using the energy balance, I can kind of illustrate how the pressure drop and friction are related when I have simple flow through a pipe. But the next question becomes, how can I relate this pressure drop to the shear stress which causes it? Well, if we recall from our discussion on momentum, tau W is equal to delta P times diameter over 4 times length. Which means if I combine these two expressions, oh, sorry, cut out. I have tau W oh, I'm missing an expression. I can say tau W or sorry, solving for delta pressure. Delta P is equal to 4L tau W over diameter. And so with these two expressions, I can solve for either shear stress or pressure drop. However, most often than not, what we're really looking for is a way to calculate energy dissipation either through measuring pressure drop or through quantification of other process variables, which means we have to identify a new way to describe our frictional dissipation and energy loss in our flow system. And we do that through the use of a new term or parameter, which is known as our friction factor. And the friction factor quantifies the energy dissipation due to fluid flow as a function of shear and kinetic energy. We designate this value as f, like fancy lowercase f, as opposed to fancy uppercase F, and it's defined as shear stress divided by fluid density times the flow velocity squared over 2, which if I rearrange this, I simply have 2 times the shear stress over density times velocity squared. So now with this in mind, and looking at my expression for shear that I have developed above, when last we talked about momentum balance, we defined that expression. I can solve for shear stress and say that it is the friction factor times density times velocity squared divided by 2. And knowing that shear stress is also the change in pressure times diameter divided by 4 times the flow length, if I can combine these two expressions, what I'm left with is the friction factor times density velocity squared over 2 equals the change in pressure in our system times the flow diameter divided by 4 times the length, or the pipe length. Which means if I want to solve for pressure drop now, what I'm left with is 2 times the friction factor times the density times velocity squared times the flow length over diameter. And this is an extremely important expression because now, through use of a friction factor, which I can estimate, I can directly solve for an expected pressure drop from skin friction. And if I wanted to solve for pressure drop per unit length, it's simply 2 times the friction factor times density times velocity squared over diameter. And if I wanted to solve for pressure drop over density, because that's the typical form we see it in the energy balance, it simply looks like this. So definitely keep these expressions in mind because they are extremely important as we quantify frictional dissipation. If I have a flow-through system, any skin friction as a result of shear, we can quantify it using these expressions. Is there any questions? Any things I can further clarify or re-explain? Just as a quick recap, what we've looked at is the emergence of shear and how it results in a pressure drop. From our momentum balance that we did in our last lecture, we were able to quantify that shear and relate it to pressure drop. However, the issue comes is there's no real way to measure shear stress. And so if we have a new parameter which we can obtain via a friction factor that we can quantify, then we can directly calculate and estimate frictional dissipation due to shear stress by essentially eliminating the term from our expressions. And what we're left with is this general expression to calculate pressure drop as a resulting from shear stress. All right, if there's no questions, let's take a look at an example. And this example asks to determine the pressure loss or pressure drop per unit length of pipe for ethanol with a specific gravity of 0.79 flowing at 10 feet per second through a 3-inch Schedule 40 pipe, assuming our friction factor is 0.005. So for this, looking at this example, we want to estimate our pressure drop per unit length for ethanol. The specific gravity is 0.79, flowing at 10 feet per second through a 3-inch Schedule 40 pipe, which gives us a diameter of 3.068 inches, assuming our friction factor is 0.005. So I would go up to this version of my expression. Delta P over L is equal to 2 times the friction factor times my fluid density times the velocity squared divided by the diameter. So delta P over L is equal to 2 times 0.005. Now the friction factors will be unitless, so keep that in mind when doing your calculations. Then we have our density, which is 0.79 times our reference fluid, which is going to be water, or a density of 62.4 pound mass per cubic feet, times velocity, 10 feet per second squared, divided by the diameter, 3.068 over 12 feet. Now, if we do this and we look at our units, what we're left with is pound mass per, I think, what is it? Feet squared, second squared. So we're going to have to do some unit conversions. So if I divide by 32.2 pound mass feet per pound force, second squared, and then I divide by 144 inches squared and a foot squared, this will leave me my answer in PSI, or pound force per inch squared per foot. In doing that calculation, I should get approximately 0.04 PSI per foot. So hopefully that felt pretty straightforward. However, it will get a little trickier as we move on. The next question I have for you guys is this one. So the question asks, in general, increasing the Reynolds number decreases the friction factor for a given fluid traveling in a pipe. So what do you guys think? Does increasing the Reynolds number increase or decrease our friction factor? Any takers? You guys are quiet today. You think the friction factor increases? I appreciate your participation. Anyone else want to chime in? Or you have no idea?
No idea.
Okay, I could be honest, there's nothing wrong with that. So in general, when we're looking at these systems, what we'll find out here shortly is increasing the Reynolds number will decrease the friction factor. However, the result frictional dissipation will increase as a result of increasing our Reynolds number. And so this one's kind of designed to be a tricky question, but it's really just not as tricky as I'd originally anticipated, because what we'll see is that friction factor, while related to the actual frictional dissipation, it doesn't tell the full story. So with that in mind, now that we have this generalized expression for frictional dissipation due to skin friction, let's look in depth or a little more closely at our two flow regimes of interest, namely laminar and turbulent flow. Yeah, just got to find the right. All right. So looking at laminar flow. So if we can recall from transport, hopefully, that laminar flow primarily holds a parabolic velocity profile, which looks something like this, with the maximum flow velocity occurring at the center of our flow system. Also, we previously discussed that for Newtonian fluids, we can relate shear within our laminar flow as a function of the fluid viscosity and the velocity gradient that exists within our flow system. And so from this, theoretically, if we were able to integrate this system, we would get a direct correlation between viscosity, our velocity, and the expected shear stress that would arise due to flow. So if we were to do that and look at, if we were to look at a thin ring within the pipe, we would be able to set up that differential relating the radius to a differential area. And from this, and combining the two expressions, we could write an expression that states the change in velocity with respect to the radius is simply the shear stress over the radius divided by viscosity times r. Where if we were to separate the variables and integrate from 0 to velocity, from the radius of the wall to any differential radius, we could obtain the following expression. And you really don't have to write this down. This is just an illustration of a derivation to get to an interesting and useful expression. So if you want to just sit back and watch, I'll tell you what's important here at the end. So we can get a description for our velocity as the shear stress divided by 2 times the radius over the viscosity times the comparison between the full radius minus any differential radius or radial distance in between. Which means what we can look at, if we were interested in solving for the radius at any point within our system, we can use this expression provided we knew the flow velocity, the viscosity, and our shear stress. Well, we do know that the maximum velocity occurs at the center, where r equals 0. So we can write mu max by plugging in where r equals 0. We can write the maximum velocity expression. And if we were to compare u over u max, we would get this simplified expression, which demonstrates a parabolic profile for velocity. And so this is kind of a mathematical exploration. It's kind of useful to a certain degree, but at the end of the day, what we're really looking for is how can we effectively describe the energy dissipation due to shear without, once again, having to solve for shear. And so what we can consider is how can we quantify our shear stress as a function of an average velocity. Which we could designate U bar, even though for most purposes in the class, when I write velocity, it's always some average or mean velocity. Well, knowing that the average velocity as compared to the maximum velocity through lots of experimentation, we find that the average is half of what can be measured at the center. We can then write an expression for the average velocity by just simply taking our maximum velocity expression and dividing it by 2, or we get tau w rw over 4 mu. And so now what we have is an expression for shear stress as a function of average velocity. Now if we take that same idea and we combine it with our expression that we obtained in our momentum discussion, which was the, where was it? Tau w equals delta p times d over 4L. Once again, what we have is two expressions that both quantify shear, but now one's looking at pressure drop, one's looking at velocity. So if I rewrite my velocity expression in terms of shear, what I'm left with is tau w equals 4 mu times u bar divided by rw. So now, once again, if I combine these two expressions, what I'm left with is 4 mu u over rw equals delta p times d over 4L. Now, knowing that rw is equal to just the diameter over the length, or not length, excuse me, over 2, because math, I can plug that in, and so I end up with 8 mu u over diameter. I'm getting out of u bar, because once again, in this class, everything's just kind of, so now I have 8 times the viscosity times our velocity divided by diameter equals the pressure drop times diameter over 4L. And then, once again, what we really want to know is our pressure drop. So plugging this in, I'm left with 32 times viscosity times velocity times the flow length over diameter squared. And this is an extremely important equation, which has its own name, which is the Hagen-Poiseuille equation, which gets all the fanfare. And so this expression describes the pressure drop that we see due to skin friction as it occurs within laminar flow. You'll notice for this expression, we don't really need to look at friction factor. All we need to understand is what's the flow length, the flow diameter, the fluid viscosity, and the fluid velocity. And so that's an important distinction in this expression is for laminar flow, pressure drop can be quantified without having to know any sort of information surrounding our friction factor. And so, like I said, it was a little math intensive. Hopefully I didn't lose you guys in that discussion, but it is worthwhile in terms of doing that exploration of the mathematics, so you can kind of start to understand where the Hagen-Poiseuille comes from. So is there any questions on how I was able to do that derivation and the end result? If not, let's go jump and look at another example, which is primarily this one, looking at determining the pressure drop per unit length for fluid flowing through a 2-inch pipe at a flow rate of 0.5 feet per second if the viscosity measured is 1.2 times 10 to the minus 2 pound mass per feet second, and the fluid density is 36.2 pound mass per feet cubed. And the last part, which we'll discuss after we do the calculation, is how does the pressure drop per unit length change if we increase the fluid velocity to 1 feet per second and 2 feet per second. All right, so for this, what I'm gonna have you guys do is work together in some breakouts for a couple minutes. And also what I would like you to do is when you get a solution, come on back and go ahead and essentially give me your answer in the chat along with the members of the people in your breakout rooms. So I'll give you guys about 3 minutes to work on this. How's it going, Elahe?
I'm good, Dr. Lopez. How are you?
All right. You're doing your walkabout, or you at campus or home?
I'm at campus,
Fun.
but I'm getting coffee.
You're good. Are you feeling better?
Yeah, I am. I went to the doctor and they told me it's allergies, so they told me to take like allergy medication every day.
That's helpful.
How are you? Everything
Pretty good? Yeah.
Okay.
Busy,
That's
hectic.
Nice.
Yeah.
It's everybody's situation, I guess.
Yeah. You can only do so much, and you just kind of have to deal the best we can. All right, I'll bring everybody back. All right. Everybody should be back in the next 15 seconds. Let's see. Welcome back, everybody. As you get flung into the void and then flung back. So how did the problem go? Did we get an answer?
Yeah, I got a really small number. I got 2.48 times 10 to the minus 4 psi per foot. No idea if that's right though.
Anybody, any other groups got a solution?
0.00149.
Never mind. I think it'll be, yeah, mine's wrong.
Got 0.00149 psi per foot.
All right, I did. That is what I obtained. 1.5 times 10 to the minus 3 psi per foot. Which, you know, quickly for notes purposes, which can be solved by plugging into the expression, which is a rearrangement of Hague-Purcell, which ends up being 32 times viscosity times velocity over diameter squared. So if you plug in the values, you get something that looks like this. Feet per second divided by 2 over 12 feet squared, which once again, you have to divide by 32.2 pound mass feet per pound force second squared, and also by the conversion of feet squared to inches squared.
Dr. Lopez, isn't the mu factor supposed to be 0.012, not 0.12?
Oh yeah, sorry, I forgot the 0. Thank you.
The question is, you don't have a foot. LBM feet squared.
So we have 32 times 0.012 times 0.5 divided by 2 divided by 12 squared, and then divided by g sub c, 32.2, and then divided by 144. And this should give you, like I said, 1.5 times 10 to the minus 3 psi per foot. So then the last part of the question asked, what would we expect to happen for our pressure drop per unit length if we doubled the velocity?
If we double the velocity.
Yes.
It would increase.
It would increase to what?
0.00298, I think.
So yeah, the pressure drop would double to 3 feet, 3 times 10 to the minus 3. And you know, if the velocity doubled again, the pressure drop per unit length, I apologize for my handwriting this morning. It would double once again to 6 times 10 to the minus 3 psi per foot. So this tells us when we're looking at frictional dissipation and pressure drop in laminar flow that we have a linear relationship between our energy loss and our pressure drop when we're considering both viscosity and velocity. Now, one other thing I want to touch base on in terms of laminar flow is our exploration in math gave us this expression, mu u over d, to describe shear stress. If we consider the definition that we had obtained for frictional dissipation, excuse me, friction factor as it relates to shear, we ended up with this expression, right? And what we can do here, if we want to consider how laminar flow and friction factor are related, we can combine these two expressions such that we're left with 8 mu u over d equals rho u squared f over 2. And if we were to solve for our friction factor, what we're left with is 16 times mu over rho u d, which hopefully this may look familiar. So what is that grouping?
The inverse of the Reynolds number.
Correct, which tells us to find a friction factor in the laminar flow, it's simply 16 divided by the Reynolds number. Which then, if we were going to go back to the question I asked earlier, we see that increasing the Reynolds number decreases our friction factor. Even though increasing the Reynolds number, i.e. our flow velocity, would result in an increased pressure drop. So keep this one in mind. It's a good way when you're looking at solving for frictional dissipation in terms of friction factor to just simply use Reynolds number in our earlier discussion. All right, now let's switch gears and talk about frictional dissipation and turbulent flow. And so turbulent flow differs highly from laminar flow in a lot of ways in how frictional dissipation can be quantified. Oh, I think I just lost something. What happened? All right. So in general, in turbulent flow, a very thin, I shouldn't say a very thin, it's just bad writing. A thin boundary layer exists between the wall and the majority of flow. Such that if I was going to look at my velocity profile, our parabola, excuse me, breaks down, and what we typically see is more kind of a very thin profile that happens close to the wall, and then and in general a pretty flat average that exists within the majority of flow. Primarily because when we consider turbulent flow, there's a lot of flow irregularities, which fortunately hovers around a mean, and so it may in reality look kind of messy at any given point, but at the end of the day we really don't care what the instantaneous velocity is at any one point. We're not trying to be mathematicians, we're just trying to do something with it. And so the mean works a lot more effectively. And so what that tells us is that our velocity distribution in general is more even as compared to laminar flow. Thus, the friction factor will be much lower in turbulent flow. Wow, I cannot spell today. However, the frictional dissipation will be much higher, or higher, as compared to laminar flow. And so what we typically see is that in laminar flow, our friction is directly proportional to the product of our flow velocity and our flow viscosity. Meaning viscosity is important when we're calculating frictional dissipation in laminar flow, and so is our velocity. However, in turbulent flow, we find that the frictional dissipation is a function solely of velocity, but the square of the velocity. And so you can kind of see from this is that increases in flow velocity will have a much more dramatic effect on our energy dissipation that we see in turbulent flow as compared to laminar flow. And at the same time, our frictional dissipation becomes independent of our flow viscosity. Primarily because when we consider that shear stress that occurs at the wall, the contribution of shear and energy dissipation often occurs due to the vortices and irregular flow and the mixing and all those kinds of phenomena that happens within the fluid. And so that becomes a large portion of the energy dissipation that we experience. So the question then becomes, well, how do we calculate frictional dissipation similarly that we do in laminar flow? Well, the short answer is it's more complicated in turbulent flow, primarily because there's a couple things we must consider beyond simply just looking at the friction factor. And the other important parameter that we must consider is our surface roughness, which is a quantification of anticipated shear which would occur at our solid fluid interface. And essentially what that means is the more rough that we see as a material or a surface, the more likely we're going to see flow irregularities within our system. A rough surface is going to give rise to more vortices, eddies, things of that nature. And so most materials will have some form of roughness factor, which is designated kappa. And what often than not we're interested in is looking for relative roughness, which is our roughness over our flow diameter, which means our roughness value is given units of length because our relative roughness is unitless. And so for those of you with the textbook, where we're getting at is on page essentially 113 to 115 is our discussion on roughness and how it treats to frictional dissipation. And in the figure on 510, which we're going to talk about here in a second, you see a table within that that designates roughness values. And feet. For example, if we're looking at steel, any stainless steels, the roughness value, or K value, is going to be 0.00015 feet. So with this in mind, what we typically look at once we have relative roughness is we combine our relative roughness and our Reynolds number to estimate our friction factor. And we do this through use of a somewhat helpful chart, which looks like this. And then you'll find it, once again, it's on page 115 of the textbook. And you'll notice the x-axis is a logarithmic plot for Reynolds number. The secondary y-axis on the right-hand side is, once again, a logarithmic, so to speak, plot of relative roughness, K over D values. And the primary y-axis is your friction factor, which, keep in mind, in this class, we're looking at primarily the fanning friction factor. Now, a secondary derivation for friction factor exists, which results in what's known as the Moody friction factor chart. However, the numbers and values are slightly different in terms of how frictional dissipation is calculated. So keep in mind when you're looking at friction factors and calculating frictional dissipation, which method that you're using. For this class, we use fanning friction factor because that's what's illustrated in the text. However, a lot of other texts use the Moody system, which gives you the same results. It's just some of the numbers are different. One thing you'll notice is for laminar flow, we see that's dependence that we identified earlier, where our frictional factors are high, and it can be calculated simply as 16 over the Reynolds number. As we get to our transition region, we have essentially no solid quantification until we hit to our 4,000 mark, where we start to see estimations for friction factor in turbulent flow. A couple things to note in this chart is you'll notice that as we approach a certain Reynolds number, these curves begin to level out. And that isn't done by accident. What that is here to illustrate, and it's to show you, is that once you get to a sufficiently high Reynolds number for most systems, the friction factor becomes a constant value. And essentially, the friction factor becomes fixed, and your frictional dissipation becomes entirely dependent on the flow velocity. And a couple other things to identify here. You'll notice the bottom line is known as a smooth line for something that's essentially infinitely smooth, that it has no quantifiable roughness. It'll be quantified by this bottom curve. And then as you get to more higher and higher roughness, relative roughness values, you'll move up in your expression. So let's work together to work an example on calculating some pressure drops, frictional dissipation, and turbulent flow. So let's take a look at an example. If I have 20 gallons per minute of water traveling through 100 feet of 3-inch Schedule 40 stainless steel pipe, entering at a pressure of 45 psia, what is the pressure drop across the pipe? So for this problem, I'm going to be using the original expression we developed to F rho U squared L over D, which, if I have water, the density, am I in English units? I'm always in English units in this class, which is what drives people crazy. 62.4 pound mass per cubic feet. The flow velocity was it's not provided, so we'll have to solve for it. our volumetric flow rate is 20 gallons per minute. Our diameter was provided. It's 3-inch schedule 40, 3.068. You'll notice I tend to lean into some of these. Our length was 100 feet. And we don't have our friction factor. So the first thing we should probably look at doing is calculating our flow area. Fortunately, since we have a 3-inch schedule 40 pipe, we can refer to our appendix 3 in the back of the book, and we'd find that the flow area is approximately 0.0513 square feet, which means if I want to calculate my fluid velocity, all I have to do is divide my volumetric flow rate divided by my flow area, or 20 gallons per minute, divided by 7.48 gallons in a cubic foot. And in 1 minute is 60 seconds. And then divided by 0.0513 square feet. We do that calculation. Let's see what we get. I've got about 0.869 feet per second. So now that I have that, 0.869 feet per second, I was able to calculate that. So all we need is our friction factor. To solve for friction factor, we're going to need to calculate our Reynolds number. Which the density is 62.4 pound mass per cubic feet. The flow velocity is 0.869 feet per second. The diameter, 3.068 over 12. And the viscosity of water is 1 centipoise. If I was to convert that to English, it would be 6.72 times 10 to the minus 4 pound mass per feet second. So if I do this calculation, I get about 20,600. You'll notice you don't have to be super exact with the Reynolds number because the figures that we're looking at using are logarithmic plots, and so don't expect to get very exact values in this. So we have a Reynolds numbers. So what we need next is our relative roughness factor, K over D, which for stainless steel, I said earlier, 0.00015 feet is our roughness value for steel. Diameter, once again, 3.068 over 12 feet. Those cancel. So I get about 0.0006, or I should say 59. It'll help make you feel better. For our roughness factor, which then what we need to do to get our friction, we need to go to our chart and look at the intersection of essentially 20,600 and 0.006. So I see 20,000 around here. If you guys can see that, my cursor. So I would go up to where the 0.006 line is, which should be somewhere in this mess. So I would estimate that friction factor as being approximately 0.007 was my F. Is everyone kind of seeing how I'm doing that? Oh, I need to shift it over. Never mind. Hold on. Let me double check that value. Nope, that is correct. So I went on my x-axis, I found my Reynolds number, and then I move up in the y-axis until I intersect that relative roughness factor, which I do that approximately here, which I would argue maybe a little under 0.007, probably 0.0068. Once again, these aren't going to be super exact values, which I can understand could be quite frustrating. And now that we have that friction factor, we can then solve for our frictional dissipation. So we have delta P is equal to 2 times our friction factor times our density times our velocity squared times our flow length divided by diameter, with these as the parameters.
Dr. Lopez, are you drawing? Because we can't see it.
Oh, I'm sorry, I need to jump back. I just put in that value where I had initially written all my variables out. So with that in mind, now I can go and start solving for my pressure drop, my delta P, which is 2 times my friction factor of 0.0068 times my density, 62.4 pound mass per cubic foot, times my velocity squared, 0.869 feet per second squared, times my length, 100 feet, divided by my diameter, or 3.068 divided by 12 feet. You'll notice once again, we're left in our very strange pound mass feet units. So we will have to, unfortunately, take this and divide it by our G sub C, 32.2 pound mass feet per pound force second squared, as well as converting our feet squared to 144 square inches. So we do that, and for good measure, we can double check our units. So I have, let's see, a foot here, a foot here. So I have a square feet here. I know my second square is gone here. So I have feet, what is my units there? Feet to the fourth on the top. And where do I have? Feet to the fourth on the bottom. There's 4 here, there's 4 here. So I'm left with pound force per square inch, inches squared, or PSI, or delta P. I can do this calculation. I get approximately 0.05 PSI. Yeah, feel free to double check my calculation. So from that 100 feet of flow pipe, we lose about 0.05 PSI. Any questions on that example on following the process and how this calculation occurs? Yeah, your synthesis assignment this week is going to be developing a flowchart in terms of identifying how to solve what I would consider the full-fledged fluid problems for this course, which is going to be looking at, determining power requirements for a flow system, including friction, And so those questions can get quite involved because this calculation is just a fraction of one of those problems. And so developing that flow sheet is going to be extremely helpful to you as you do both homework as well as completing the midterm, which is the big reason why I put it as this week's synthesis assignment, because I think developing that and taking the time to outline the steps for these types of problems is going to be extremely beneficial, as it will save you a lot of time during your midterms and your final. So any questions, anything I can further clarify?
By a flow chart, do you mean like what values are at different values, or like step-by-step process on what to do if this occurs?
Step-by-step process on what to do given this type of problem.
Alrighty. Thank you.
Oh, you're okay. One other thing to consider when we're looking at these systems is as the charts are very difficult to read, empirical models have been developed to estimate your friction factor for certain subsections of Reynolds number, essentially, where we see for smooth pipe, we can use the top expression. For the middle, we can use the middle expression. For and high Reynolds number, we can estimate it solely by this bottom expression. And so the question often becomes, what is more accurate, the friction factor charts or the empirical models? And the answer, as always, is it depends. And so what I can tell you is when I do these calculations and for the homeworks, I typically want students to complete these friction factor estimations using the charts, because it's just good practice using the charts. However, there's no clear answer or distinction, because the empirical models are going to work for some systems. The factor charts are, I would argue, more robust, but they're also subject to a lot more user error, because once again, I don't know what it is about engineering and having to have the most complicated figures in the world, but it's like a tournament, it seems, about who can create the most asinine chart that is quote unquote helpful. And so it's something to keep in mind, and it's something to always consider. In terms of the empirical models are there for the estimations, so is the chart. They're both going to be, quote unquote accurate to some degree. But like I said, for homework, go ahead and use the chart if you can. And on exams, I'm also going to give you the chart, because I want to see, one, your ability to read this. It's pretty good. Test type question is, can you look at something that looks this crazy and interpret it in a meaningful way? That's points on a midterm. So, all right, the next points of discussion is additional considerations for frictional dissipation within flow systems. And so what I mean by that is, up until this point, we've primarily only discussed frictional dissipation due to shear and skin friction. However, there's a lot more, or a lot other areas for frictional dissipation in flow. Primarily, there's friction due to expansion, contraction, and fittings. That's typically what I call it. So what that means is, if I'm looking at, let's say, expansion, that means I have a flow existing in one section with a particular diameter A, and it's transitioning to a much larger diameter B. And as we said, Fluid follows momentum conservation laws, which means the fluid isn't going to stop here, wait for the red light to turn green and take a left. It's just going to keep going. And so what you see is, in general, the flow is going to exist like this, which means there's dead spaces, which means the pressure is going to eventually pull fluid backwards. And so what you're going to get is vortices forming at those edges. And that vortices behavior is going to result in energy losses within our system. And we can quantify this energy loss through a correlation that looks like this, where our energy loss due to expansion, which I'm going to say H of E, which it's going to drive you crazy, but it's quantified using, head terms, as U squared over 2, where our expansion coefficient is going to be 1 minus the area of A over the area of B squared. And so you get an expansion coefficient, which is a function of the two sectional areas. You multiply that times the kinetic energy of the system, U squared over 2, and you get a quantification of, actually that's not in gravity, then you get an idea of the losses due to expansion. Now, if we were looking at contraction, something similar would occur, where now we have flow section A, flow section B, and we're going to have flow that's going to essentially be compressed, which means you're going to have vortices occur on this side, which, if we quantify, we get a contractional loss, which follows the same pattern. So F is equal to HC, which is equal to KC U squared over 2, where KC is 0.4 times 1 minus area of A, B over area of A. Which estimates what we can expect in terms of contraction losses. And the last one is fittings. Now, what I mean by fittings, I mean elbows, T's, any sort of essentially modifier to our flow system. So fitting are the other categories. Where due to fittings, we have the same expression, K sub F is equal to U squared over 2. But K sub F, it depends on the fitting. And so what we use is our handy dandy charts to estimate fitting losses in our system. Which, let me share. So you can see this is in your textbook as well. And for most manufacturers of valves, fittings, you get expressions on this. But for this particular table, it's table 5.1 on page 124. And you'll see for a 45-degree elbow, we can estimate the fitting loss is 0.35 times the kinetic energy that we see in our system. And so, depending on the type of fittings, the type of valves, we can estimate the total fitting loss in any flow system, primarily just by summing up all the fittings that exist within our system. So if you got 12 T's, 15 elbows, 3 return bends, you just essentially sum them up, multiply them by the kinetic energy term, and you're left with your total energy loss due to the fittings present in your flow system. Which means if we wanted to combine expansion, contraction, and fitting losses with skin friction, you'll notice that the common denominator is this kinetic energy expression, u squared over 2. And if we look closely at our delta P expression, we have a sort of u squared over 2, which means I can write it as 4f rho L over
Dr.
D
Lopez.
times u. Yeah, I'm going to switch it back here in a second.
Okay, thank you.
No problem. I always appreciate you guys letting me know. So we have these u squared over 2 terms in our expression. And if we look at our pressure drop due to skin friction, I can rewrite it as a form of u squared over 2, by bringing out the u squared and dividing by 2, which makes that first term a 4. So you see how I was able to essentially make this the same form as expansion, contraction, and fitting losses. Which means if I wanted to solve for friction in general, what I'm looking at is skin friction, expansion, contraction, and fittings times the kinetic energy that we see in our system. And if I wanted to write it in terms of head loss, it's the same thing, but all we got to do is add gravity in the mix. So this is the full expression to quantify friction in our energy balance expression. We spend a lot of time on skin friction because primarily that's the key in terms of most flow systems, especially when you're looking at long lengths. But we also have to consider any expansion that occurs, any contraction that occurs, and the fittings that exist within our flow system. Knowing all this, we can combine all 4 of these terms together to quantify frictional dissipation when flow. Any questions on this? That's all I had for the day. I know we're a few minutes over, but like I said, I wanted to make sure you guys got to this conclusion so that you had all the tools you needed to complete your homework.
Yeah, Dr. Lopez, I have a question.
Of course, go ahead.
What units will head loss be in?
Length.
Okay.
So meters or inches. This is going to be your feet squared per second squared, because you'll notice these are all unitless in terms of values, and F is unitless. This is in terms of mass per cubic feet. These are in terms of oh, you actually might have pointed something important out to me. We might have to change the form of our frictional dissipation to match it up in our system. So to get the units to work out, it needs to be in the form of delta P over rho, which means if we were going to combine it this way, we don't need to consider our density. Thank you for pointing that out. That was going to be a very important confusion for those. So if we do it this way, now the units work out. Because when that, and this is where it gets, well, it'll get tricky when you're doing some of the calculations, primarily because density likes to disappear sometimes in these calculations. And that's why I always stress, let the units tell you what needs to exist within your equation. And so each of the expansion, contraction, and fitting losses are going to be unitless. And the friction term is going to be the same as every other term in the energy balance, meaning for just simply friction, we're looking at length squared per time squared. For head loss. In terms of fluid head, it's just going to be length. And so when we're talking about friction, we're looking more as, instead of a delta P, more a delta P over rho, which is why we're gonna need to throw out the density. So it's just something to keep in mind. If you're wanting to calculate friction as it exists, you would divide by the density. But if you're really wanting to calculate friction, but at the same time wanting the actual pressure drop, the density comes back in. So thank you for that, Claire. Hopefully I didn't confuse a bunch of people with that correction. Any other questions? I promise I'll try really hard not to make things even more confusing with my answer. All right, if not, take care, guys. I hope you all have a great week. As always, if you need anything, feel free to reach out. I will not be on office hours at 11. I do have another appointment, but I will be available this afternoon at about 1. Okay? Take care, guys. Have a great day.
Thank
Have a
you,
great
Dr.
day.
Lopez.
You're welcome.